So this section is on friction. It'll just be a short section, hopefully, and I'm just going to talk about a little bit about what friction is and how we use it, and a little bit of the physics of it. So let's start with just a look at friction. Usually we experience friction, we're trying to move something, and so this is a picture of a box here, and you're getting sort of a blow up of the microscopic interaction between two surfaces that might look visually smooth, but on a microscopic level, they're not. And so the friction is kind of the interaction between the two surfaces as they move past each other, or as we try to move them past each other. And so there's lots of interesting things that happen. First, the unevenness you can see if you were trying to push the box, which is the top piece, to the right. There's going to be a friction force to the left in the opposite direction, slowing you down. And it's because of all these interactions. Some of them are just the bumps running against each other, but some are the chemical properties of the two materials interacting with each other as they touch at the contact surface. Notice, so the friction force is a drag force due to microscopic interactions between the two surfaces in contact. The friction force depends on the types of materials. So if the top piece was, instead of a box, if it was a block of ice and the bottom was Teflon or something like that, you might have a very different friction force, even though the object was the same size and weight as this box is sitting on some carpeting or something. I don't know what that is, linoleum maybe. So in the case if you're dragging a concrete block across a dirt road, it's different than dragging a sled across a frozen lake. Right? They might weigh the same or be close to the same size or something like that, but the materials matter too. Note the friction force is always parallel to the surface, and so it's always it's always opposing the direction of the applied force. And so here the box is being pushed to the right, but the friction force is being pushed to the left. And the friction force depends on what we call the normal force, which I've mentioned before, and we'll talk about a little bit here. So this is a good example of sort of how we view the normal force. In the figure at the top, in part A, you can see the person is holding I don't know what that is, Bow Wow Chow, a bag of Bow Wow Chow. And if it's being held stationary, then there are two forces acting on the Bow Wow Chow. One is its weight, the gravitational force, and one is the force from the person's hands holding it up. If it's being held stationary, we know that the net force is zero, and since those are the only two forces acting, they must be acting with equal magnitude and in opposite directions, because the net force has to be zero. They're pushing the opposite way. If the Bow Wow Chow is then set on the table, the same thing has to be true as long as it doesn't fall through the table or something like that. If the Bow Wow Chow is just sitting on a table, or anything is sitting on a table, or anything is stationary anywhere sitting on a surface, then the weight of that object, which is the earth pulling down on that object, has to be balanced by an upward force that exactly cancels it. That's the force we call the normal force. And anytime something's sitting on a surface, it has a normal force acting on it to counterbalance all the other forces that are acting. And so if there could be 6 forces acting on this, there could be people pushing in different directions or all kinds of other things happening. In this case, we've got something fairly simple. We've got just the weight, and so the normal force has to exactly oppose the weight so that the Bow Wow Chow doesn't fall through the table, and that the net force is zero on it so that it's stationary. So the friction force depends on this normal force. The normal force is how hard the contact surface is pushing up. In figure A, we see the Bow Wow Chow is balanced by the person's force. In B, it's balanced by the normal force. Since the bag of chow is motionless, we know that these two forces must be equal. Generally speaking, if you just have an object sitting on a surface, then the normal force is equal to the weight. It gets a little trickier if the surface is slanted or if somebody is also pulling on the object. For example, if this person were to come over here and lift up just a little on this Bow Wow Chow so that it was still on the surface but was pushing down less hard on the surface, and the surface would push up less hard on the box, and the normal force would be less. Push up less hard on the bow wow chow. All right, we'll talk about that some more as we go. So how does friction and the normal force interact? Well, if you look at this picture, you can sort of see that for a lighter weight object, the two surfaces are pressed together a little less than for a heavier object. If the lower figure is a heavier objects tend to push themselves into other surfaces. The weight of the object is pushing down, the normal force is pushing up. These two kind of crush the object in between, and so they reduce the size of that space. That increases the friction force. And so the figure above shows why the friction force depends on the normal force. The greater the normal force, the greater the friction force. That usually means the heavier an object is, the greater the friction force it's going to experience, because heavier objects have greater normal forces. One way you can reduce the amount of friction on a heavy object is to lift up on it as you drag it. And so let me show a picture. So imagine this is a surface, right? And I'm dragging pushing a box along a surface this way, right? And so I would have my force this way, and then this way here would be the friction force dragging against me, right? This force depends on the normal force, right? Well, the normal force is just the force that's balancing the weight. Ooh, sorry. Normal force is balancing the weight, right? These two are the same. Well, if while I'm pushing this, someone were to lift up on the box a little bit, that reduces the amount of weight here and would reduce the normal force. So I could have a little F here, so I could say F help, right? That would mean that the amount of weight this surface would feel would be smaller because it's being lifted up on it, so it wouldn't feel as much of the weight, and so then you would have a smaller normal force, and that would reduce the friction force. I usually call those F-sub. So often, if you find yourself dragging something, usually lifting up on it to drag it will help you, because it'll reduce the amount of friction. Okay, so a couple of things. If there are no lateral forces on an object, then the friction force is 0. So if I go back to this picture, right, let me just erase this for a second and say, look, if my cup is sitting on the table, right, here's my cup again. I always have my cup. Right, here's my cup. It's got the weight, and it's got a normal force acting on it, acting at the surface, right? If nobody's pushing on it horizontally, then there's no friction force. It's only when I start to push it that I get a friction force opposing me. And so a stationary object doesn't generally have a friction force. The exception to that, of course, is that I could be pushing on this but not hard enough to move it. And then there would be a friction force that would be just balancing my push force until I push hard enough to get it going, and then it's got a steady friction force. But as long as there are no other forces acting, as long as nobody's pushing on the outside of this cup, the friction force on it is 0. It's also true that if there's no normal force, there's no friction force. If somehow I can make a surface somehow I can make this thing float above the surface so that the contact force is 0, there's no normal force, then there won't be any friction force. That's actually done sometimes by, or nearly done sometimes, by, for example, if you've ever played air hockey, right? On an air hockey table, what they do, let me see if I can go back to this disc, right? If I look at an air hockey table from the side, here's a hockey puck, here's an air hockey puck, and then there's these little holes, right, that are blowing air out like this. And so they lift the puck off the surface, and so there's no drag, or extremely low drag. And so So you can effectively say the normal force is zero. What in fact is happening is that the weight is balanced by a wind force that's pushing up rather than by the normal force from the surface. And that wind force is much smaller for drag. So if the surfaces are pretty smooth and non-interacting, you can have a normal, a normal force without a friction force. This is, excuse me, this is really important in industry. Sometimes when you have motors and things like that with moving parts and you want as low friction as possible in a car engine, for example, there's a normal force, but you don't want a friction force, or you want to have as minimal a friction force as possible. You're often after that. And material scientists work very hard at this, and you hear about materials like Teflon, but even other surfaces made of metals that are extremely low friction are constantly being developed. Metals and other materials. And so how we use friction. So friction is really interesting because sometimes we don't like it and sometimes we do like it. The way we walk is by pushing backward on the floor. Stand up and walk around a little bit and you'll sort of see, maybe if you haven't thought about it. This requires a friction force to walk. If you think it doesn't, try walking on a slippery surface and you'll see what I mean. Certainly some wet ice is about as slippery as you can get. But when you walk, what you do is you push backwards with your foot. Now, if you go through the whole process of like taking a step forward and landing on your heel, right? And so that's one way people slip, because you're kind of pushing forward with that foot as you land. But then as you roll over that foot is pushing backward, and that backward push is what moves you forward. And so when there's friction between your foot and the ground, I guess I'm here, your foot pushes backward on the ground. So by Newton's third law, right, if your foot pushes backward on the ground pushes forward on your foot, and the ground pushes your foot, and by extension your whole body, forward. It is this friction force that moves your body forward. And so when you're running or walking, it's the ground that's pushing you forward. You're creating that forward force by pushing backward first on the ground, but it's the ground that's pushing you forward. Same thing with a car. The engine in a car tries to turn the wheels so that the wheels are pushing backward on the ground. The friction force then pushes forward on the wheel. And so you've heard the expression where the rubber meets the road, maybe. That says, maybe you heard the expression where the rubber meets the road. That's where the action is on a car, how it speeds up, how it stops, and so on. When you step on the gas, it tries to turn that wheel, and that pushes a backward force on the ground, which puts a forward force on the wheel, and by extension the whole car. And if you've ever tried to drive on ice or snow or gotten stuck in mud or something, you know that friction force matters. A few other friction-like forces. So air resistance is one. If you ever stuck your hand out the car window, you can feel that. You should never do that. I'm not recommending it. If you jump out of an airplane, I'm also not recommending that. A skydiver will fall until they reach what's called terminal velocity, and that's when they're going at their maximum speed. And so the drag forces are balanced against the weight. Your weight is, Earth is pulling you down, the drag forces are pushing you up, and so they're balanced, and so that's the maximum speed you can reach. Let me just draw a picture of this for a second here. Let's go back to this. So here's a skydiver, right? I don't know how to draw a skydiver. So this is somebody who's falling this way. I'll have them smiling, because how could you not be having fun if you're skydiving? Right? And so they're falling in this direction. And so this is their weight that's pulling them down, right? And then there's a drag force, an upward force, F drag. And when they're going slow, just like if you stick your car out of the window when it's going really slow, you don't feel much wind resistance. But as you speed up, this force gets greater and greater and greater. Eventually, you've sped up enough so that the drag force equals the weight. And then you stop speeding up. And that's called terminal velocity. So for a human, terminal velocity is about 100 miles an hour or so. If you're in this position, if you ball up, you can go faster. But if you just spread out, stick your arms and legs out, you'll fall at about 100 miles an hour. What's interesting is smaller animals have a smaller terminal velocity for reasons I won't really go into. But the smaller you are, the smaller your terminal velocity. So a mouse, it turns out a mouse is about the largest animal whose terminal velocity won't kill it. Now, there are animals that can do tricks like cats who can jump out of an 8-story building and sometimes survive. But generally speaking, a mouse is the size where if it falls out of an airplane, it'll land on the ground and won't die. And so what's interesting about that is if a mouse is being chased, it'll run off any surface. It'll run off a table or a building or anything if it's being chased. Most other animals, when they come to the edge of a cliff, will peek over and see how high the cliff is before they decide to jump. But if you're a little bitty animal and you're not afraid of any height, you don't mind falling 200 feet because you know it won't kill you, then you don't peek, you just run off the edge. Okay, water skiing, swimming, these are also friction-like forces. We'll actually talk about some of these again in astronomy, not so much water skiing, but drag forces in airs and gases and stuff like that where planets form. So just a few questions. Suppose you're pushing a box across the floor and somebody sets a second box on top of it. How does that affect the friction force and why? And what could they do instead? Suppose they were trying to help you. Instead of putting a second box on it, how could they help you reduce the friction? If a cup is sitting by itself on a horizontal tabletop, what's the friction force acting on it? Nobody's pushing on it. Can you have a friction force if the normal force is 0? And then give some examples where friction is useful or where you might want less friction.